A quadrilateral is a four-sided polygon. A quadrilateral is classified as cyclic if all four of its vertices lie on the circumference of a circle. Therefore, ABCD is a cyclic quadrilateral, because all four of its vertices, A, B, C, and D, lie on the circumference of a circle. There are three basic properties of a cyclic quadrilateral. The opposite angles of a cyclic quadrilateral are supplementary. The exterior angle of a cyclic quadrilateral equals the opposite interior angle. And the angles in the same segment of the circle are equal. Let's look at each property in more detail. If a quadrilateral is cyclic, then the opposite angles of the cyclic quadrilateral are supplementary. In other words, the opposite angles of a cyclic quadrilateral add up to 180 degrees. ABCD is a cyclic quadrilateral, because its vertices lie on the circumference of a circle. Therefore, because ABCD is a cyclic quadrilateral, angle A plus angle C equals 180 degrees. And angle B plus angle D equals 180 degrees. If a quadrilateral is cyclic, then the exterior angle of the cyclic quadrilateral equals the opposite interior angle of the cyclic quadrilateral. Because ABCD is a cyclic quadrilateral, angle C1 equals angle A. To illustrate the third property of cyclic quadrilaterals, we will join the diagonals, forming angles in the same segment, which was introduced with the angle at the center theorem. If a quadrilateral is cyclic, then the angles formed in the same segment of the circle will be equal. Thus, because ABCD is a cyclic quadrilateral, angle A1 equals angle B2. Chord DC subtends angles A1 and B2 at the circumference of the circle. Angle A2 equals angle D2, as these angles are subtended by chord BC. Similarly, angle C1 equals angle D1. And angle B1 equals angle C2. In order to prove that a quadrilateral is cyclic, we need to prove that any one of these properties are true. If one of these properties are true, then the other two properties will also be true. We will get to that in a bit. We will first prove these properties.